Now let's use determinants to solve this system. Now we do know that we could solve this system by graphing, by the substitution or the elimination method. This is just an alternate way of solving it. What I'm going to do is begin by creating a determinant D, which consists of the coefficients to the left of the equal sign. So the x coefficients are 4 and 3, and the y coefficients are 1 and -5. I will then evaluate this determinant, the first diagonal having a product of -20, the second diagonal having a product of 3, but I'm going to change that to a -3 so I can add these together and get -23 for the value of D. Now I need to create two more determinants, dx and dy. dx is going to use the -1160 in the first column, and dy is going to use the -11 and 60 in the second column, in the y column. Now in dx I filled in the first column. I need the second column, which is the 1, -5 from the original problem. And in dy I'm missing the first column, which will be 4, 3 from that first problem. First setup of equations. So let's evaluate each of these. In this first one we're going to have 55 for a diagonal and then -60 after I change signs, leaving us with -5 for dx. And in the second one the first product is 240. The second one will be +33 after I change the signs, and we will have 273 as the value of that determinant. Now Kramer's rule says that the solution set that we're looking for will be of the form dx over d, comma, dy over d. And if this was a 3x3 situation, we follow that by dz over d. So we will have as our solution set -5 over -23, comma, 273 over -23. And I don't like those two negatives right there, so let's rewrite this as +5/23, comma, -273/23. Now what's nice about this Kramer's rule system is it works very well with fractions because we did not see the fractions until the very end. This would not have worked well with the graphing method because you'd never be able to identify that point precisely. And with the algebraic methods we've learned thus far, it's really no fun getting these ugly values out for fractions and having to substitute them back into the original problem to solve for the other. So this method is ideal when the solution sets are rather messy. Now let's apply Kramer's rule to a 3x3 system of equations. And again, I start with D, which consists of the coefficients to the left of the equal sign. And just be careful as you're doing this that you don't change any signs accidentally. And then I'm going to bring out the coefficients from these first two columns. Then we're going to multiply each of the diagonals. The first diagonal, 1 times -4 times 3 is -12. Second one, 3 times 6 times 9 will be +162. And the third one, 5 times 2 times -6 makes -60. And adding across we get 90. Now we multiply upward for each diagonal. The first one would be -180, but it changes to +180 after I change the signs. Second diagonal would be -36, but instead we change that to +36. And the third one would be +18, but it changes to -18. Adding across we get 198, and adding the top and bottom together we get 288. Now, I always do determinant D first because this is the most important number in this system. Because as we start to go and solve our system using Kramer's rule, this value is going to be in the denominator each time. If that value is 0, then we're dividing by 0 and we've got problems, and this Kramer's rule does not work. But 288 is not 0, and that tells us we should continue on with the problem. I next like to set up dx, dy, and dz Separately, I know this takes a little space here, dx is going to contain, well actually all three of these are going to contain 9 values, and I like to go straight to this coefficient column, 6, 14, 3, and substitute them in where they belong. In dx, the 6, 14, 3 belongs in the first column. For dy, 6, 14, 3 belongs in the middle or y column. And for dz, these values 6, 14, and 3 belong in the third column. Then I go in and fill in the missing numbers. For dx, I'm missing the y and z columns, so I will fill them in 3, -4, -6, 5, 6, and 3 accordingly. And for dy, I'm missing the first and third columns, so 1, 2, 9, 5, 6, 3 accordingly. And please pay very close attention to your signs. You don't want to make any mistakes by missing a sign, because those are very difficult to find those errors. Now, one of the values or nice things about doing these by video is you can check the numbers very quickly. I'm going to do these very fast. For dx, first diagonal downward, we get -72 followed by +54 followed by -420, and those add up to -438. Multiplying upward, we get 60 plus 216 minus 126, which is 150, and adding those two together we get -288. We stop there and we see that it is good, because that tells us we're going to have a nice clean value for x when we put the -288 over the +288. So here we go for dy and dz. For values across the bottom, 42 plus 324 plus 30, adding up to 396, and I recommend that you check each of these by pausing and stopping your video. Multiplying upward and changing the signs, we have -630 minus 18 minus 36 equals -684. And adding these together, again we get -288, which is a nice number for us to see. For dz, our numbers across the bottom will be -12 plus 378 minus 72, adding up to 294. And across the top, 216 plus 84 minus 18, adding up to 282. These top and bottom values add up to 576. And now we are ready to assemble our final solution set. Kramer's rule says we are looking for dx over d, dy over d, dz over d. And that tells us we will have 288 as our value for each denominator, because that was our value of d. And our three numerators, dx is -288, as is y, and then dz is 576. Reducing these fractions, we have the solution set -1, -1, 2, which is very checkable by substituting it into the original problem. Now, this may not be your method of choice. Most of you might prefer the algebraic method of addition and eliminating variables, but if you find that this is more successful to you and you don't make mistakes with your signs and your arithmetic, this is a very good method to use to solve systems of equations.